Okay, so this is the final exercise. There are 5 parts, of which this is the first one. So before we see the other parts, we are going to solve this one. And these are puzzle problems which need Diophantine equations for their solution. So let us see what the first one is. This problem is due to Alpine of York, and here 775 means it's the year in which this problem was posed. 100 bushels of grain are distributed among 100 persons in such a way that each man, that crowd has men, women and children. Each man receives 3 bushels, each woman receives 2 bushels and each child receives half bushel. How many men, women and children are there? So we have to first of all formulate the problem by naming the variables. So let there be m men W women and C children. It's easy to remember which variable represents what if you use the first letter. Okay, like this. Then it's given that there are 100 persons in total. So that means M plus W plus C is equal to 100. So that is one equation, but we have other things also. Each man receives 3 bushels, each woman 2 bushels and each child receives half of a bushel. And 100 bushels are there and they have been distributed completely. So that means 3m plus 2w plus C over 2 is equal to 100. So we get this other equation. Now if from these two equations one removes the variable m, you know how. Then one gets from these equations, you eliminate the variable m. For example, here in place of m you can put 100 minus w minus c. Then you will get, that will result in an equation that has only w and c. From these two equations we are going to get an equation having only w and c, which then you can solve by the theory of Diophantine equations. This is the equation we get: 2w plus 5c equal to 400, and the general solution to this Diophantine equation is this: w equal to minus 800 plus 5t and c is equal to 400 minus 2t. where of course t is any integer. T is coming from the set of integers. But these variables represent quantities that cannot be negative. So for non-negativity, we must have both these expressions non-negative this should be greater than or equal to 0 and 400 minus 2t also greater than or equal to 0. These inequalities give us these requirements on t. 160 less than or equal to t less than or equal to 200. For each value of t in this range, we are going to get a value for w and c and a corresponding value for m. So all the t's that you see here are going to give us solutions. So we will get many solutions, many sets of men, women and children. So we can write like this: for each value of t in this range, we will get a solution which you can write like this as a triple of number. So that is one solution. For example, if t is say 161, this is an arbitrary choice. If you want, you can take t equal to 160. In fact, you have to take all the possibility values. Each one of them is going to give you a solution, but just for the sake of showing how a solution, how an actual solution looks, so we are taking this value, say. So if I do that, then the corresponding solution this is 17, 5 and 78. So you can have 17 men, 5 women and 78 children and have that type of distribution of grain. So that is the solution to part A. Now let us see part B. Part B is Mahavir. Oh, okay, this name is an Indian name. Mahavira Karya. From 850. There were 63 equal 63 equal piles of plantain fruit put together and 7 single fruits, 7 extra single fruits. Okay, they were divided evenly among 23 travelers. Among 23 travelers, what is the number of fruits in each pile? And hint is given, and in fact in the hint the entire thing itself is given. So the hint is just this: consider the Diophantine equation 63x plus 7 is equal to 23y. But before considering the equation, we have to write what x and y are. So the solution, it starts like this: let there be x fruits in each pile, and each traveler got y of them. Have I phrased it correctly here? Let me just once again read the question. There were 63 equal piles of plantain fruit put together and 7 single fruits. Okay, they were divided evenly among 20. Okay. So let there be x fruits in each pile, and let each traveler get y of them. Then like the hint, 63x plus 7 is equal to 23y. And both sides measure the total number of fruits, taking everything together. Or because we want to write things in a manner that we can identify what the Diophantine equation we are talking about. 23y minus 63x is equal to 7. Now this particular type of equation, we have already said something about such equations in exercise 4. By, you go back to exercise 4, you will see there that we have in fact found out that such equations have infinitely many positive solutions, and here we want positive solutions. There are infinitely many positive solutions to this Diophantine equation. And they are, these solutions are given by these formulas. X is 28 plus 23t and y is 77 plus 63t. You are being asked to conclude this on your own. At least you you go back to that theorem. We are consistently using only one theorem, right? That theorem tells us what the general solution of a Diophantine equation is. So we are just using that. So I am not going back to how we are getting this from that theorem. That we have done enough number of times. Where now because we are at once saying that there are infinitely many positive solutions, so here we won't say that t is an arbitrary integer, but we will consider only those t's that will give us positive solutions or non-negative solutions. So if you impose the non-negativity condition to these two expressions, then it turns out that t has to be an integer greater than or equal to -1. Oh, but I should also mention that okay, t is an integer, that has to be mentioned, because this means t is any real number greater than or equal to -1. We are not going to consider fractions. So that is just it. These are all the solutions. And when we are saying that these are all the solutions, that itself automatically answers the question. Why? Because we are being asked to find out the number of fruits in each pile, and that is x. So this is how x looks. Any t that you are going to choose, starting from -1 and then choosing the higher and higher values, say you take -1, you are going to get 28 minus 23, so you get x equal to 5. Then you take t equal to 0, you get x equal to 28. So all these numbers you are getting are possible number of fruits in each pile. Okay, so that way you are going to get infinitely many numbers. Each one of them is an answer to this problem. Next, C. Yen Kung. and the year is 1372. So this is from China. We have an unknown number of coins. An unknown number of coins. If you make 77 strings of them, you are 50 coins short. But if you make 78 strings, one more, it is exact. How many coins are there? And hint is given. If n is the number of coins, then n is equal to 77x plus 27, that is also equal to 78y for integers x and y. So accordingly we are going to start the solution. Let n be the number of coins, then n is equal to 77x plus 27, that is equal to 78y for some integers x and y. So note that actually it's not our aim to find x and y. That is not what we want primarily, but we want n. But in order to do so, we have to find x and y. So that's why here we are not saying what x and y specifically measure. They are just some integers that make this thing happen. So we now have the Diophantine equations 78y minus 77x equal to 27. whose general solution we can of course write, and from there we will know what capital N is. Whose general solution is this: y equal to 27 plus 77t and x is equal to 27 plus 78t, where t is an integer. So we know what n would be. N is 78 times y. So if you use this expression for y, you then get this. That is 78 times 27 is this, and 78 times 77 is 6006, and along with that you have t. But now you know what type of t you need. Note that t cannot be negative, because if you have t negative, then n becomes negative, because 6006 is greater than 2106. So you need t to be non-negative, greater than or equal to 0, and each such t gives us a solution, a possible number of coins. So you get, here also you get infinitely many solutions, and that is the solution to this part C. Then part D. This is by Christoph Rudolph. (1526). So we are nearing the present. Nearing the present time means we of course won't have any question like this posed by someone who is still alive, but after Christoph Rudolph we have the last one is due to Euler. So this one is, it goes like this: find the number of again men, women and children. Men, women and children in a company of 20 persons. If together they pay 20 coins. Why would a crowd of men, women and children would pay? Maybe they went somewhere, maybe to a fair where they are paying for some ride or something like that. 20 coins, each man paying 3, each woman 2 and each child half. Oh, so it's like that one. So then what? Oh, find the number of men. Okay. Let there be, again like before, m men, w women, and c children. Then there we had 100, I think, and here we are having 20. So m plus w plus c is 20, and also 3m plus 2w plus c over 2 is 20, because there are 20 persons in total, and also they pay 20 coins together. From these equations, we get we will get the left hand side, I think, identical to what we previously had. Yes, 2w plus 5c. But the right hand side here is different, it is 80. So that means we have again eliminated m from both the equations. The general solution to this Diophantine equation is, here the general solution looks like this. W is minus 160 plus 5t, and C is, the number of children is 80 minus 20 minus 2t, where t is an integer. For non-negative solutions, we must have this and also this. These inequalities give us an interval in which t will lie. Interval means an interval of integers. And that interval is going to be okay. Now after this, you know what you have to do. For each value of t, for each integer t satisfying these inequalities, that is 32, 33, 34, all of these things, all the way up to t equal to 40. Each one of these values is going to give us a w and a c, which are non-negative. But then corresponding to each such set of w and c, you have to find m, the number of men. Now it is up to you to see whether the m's that you are getting are actually non-negative or not. Some of them will not be non-negative. Some of the m values will be negative. So the values of w and c corresponding to which you are getting a negative m, obviously they cannot form a solution. So you have to discard those sets of values. The other values, whatever you are getting for which m is non-negative, they are going to give you legitimate solutions. So after this, I am just leaving this place blank for you to complete this. You will see that most of the t values are going to give you negative m values. So they are to be discarded. And finally, let us see this fifth part due to Euler. And in 1770. Divide divide 100. So Euler's question or puzzle is entirely mathematical. Mathematical entirely in the sense that he is not giving us women, children or fruits, nothing like that, just simply integers. Divide 100 into two summands such that one is divisible by 7 and the other by 11. Let the two summands be. So you want one of the two summands to be divisible by 7. So that means it's a multiple of 7 and the other one is a multiple of 11. So we can take like this, where x and y are integers. They are coming from the set of integers. Then because they are summands which together give us 100, so we are going to have 7x plus 11y equal to 100. So this becomes a Diophantine equation which now we have to solve. And the general solution is this. is, so we are going to have these two things. X is minus 300 plus 11t and y is 200 minus 70. Where t is an integer. Okay, I noticed one thing just now. After this, naturally what we do normally, what we have done in the other parts and also in other problems which somehow relate the variables to something physical, like counting some things or something like that. But naturally after this stage we go for non-negativity or positivity. Here also I have done this, but we don't really need that here. No? We just need two integers. But at the same time, there is another thing, of course, also. If we put this expression for x here and this expression for y here, for any integer t, we are of course going to get 100. Okay. Now I'm trying to see whether what I'm thinking is correct or not. So regardless of what the integer t is, this pair is going to satisfy this equation. And because t is an integer, 7 times x for that particular t is itself an integer, which is of course divisible by 7. Just like that, 11 times this for that t is also an integer that is divisible by 11, and their sum is 100. Okay, so this itself is the solution. So there will be infinitely many such integers. Okay. Here, however, without thinking much about what the situation is, I have gone for non-negativity, in fact positivity, and I found only one value of t, which is 28, which gives us summands 56 and 44. But we can see that there will be infinitely many. Now, I am not entirely sure whether summand means, by summands, the author or rather Euler means positive numbers only. If so, then these are the only such solutions. Otherwise, if negative numbers are allowed, then there are infinitely many. Okay. So I would stop it here, and if you just want positive numbers, positive solutions here, then these are the only things, because if you go for positivity, if you impose these extra restrictions, then it turns out that t has to lie between 27.27 and 28.57, which forces t to be exactly equal to 28, and corresponding to this t value, x is 8 and y is 4. But if negatives are allowed, then there are infinitely many. So here it ends, and here our theory of Diophantine equations and its applications also end, and the chapter itself ends. After this, we have the next chapter, primes and their distributions, which we will take up in the next number theory update. So tonight I end the video here itself, and tonight means today is Tuesday, huh? So that means our next upload is this coming Friday, and on Friday we are going to do graph theory. So see you on Friday with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.